So this is our last synchronous meeting of fall 2019. So welcome. Just a couple of reminder announcements. This is being recorded, so you've been advised. The other thing is that these will be posted on the PICUP website in the very near future. And the last thing is just a reminder, etiquette-wise, if you're not speaking, if you could sort of leave yourself muted, that helps with the sound quality for others. I'm Nick Nelson. I'm at CSU Chico, and I am the lucky winner of the Who Gets to Host This Thing sweepstakes. So tonight, we wanted to have a little bit of a discussion about what people did this semester. So we're all interested in being more computational in our classes, integrating computation further. And so I suspect all of us tried something this semester. And I'm interested, the interest for tonight is to sort of have a discussion about what did you do? Did it work? Did it not work? Why? Doesn't have to be something you tried for the first time this semester. It can be something that you tried for the 7th time and still haven't gotten it right, or 7th time and now it's completely perfect. But just sort of to talk about some ideas. So just a couple of things. We're going to sort of go around and have people share. But if you could be sure to, when you do share, talk about the course that you're doing it in. So is this, freshman level algebra-based physics, or is this, 2nd semester quantum mechanics for senior majors? And sort of give an idea of the background of your students. So, have they never touched a computer before in their lives? Are they computer science majors? Where are they on sort of the programming and physics path? So I thought I'd go ahead and start and just briefly talk about something that I've tried this semester. Oh, by the way, I was also going to mention, if you're interested, if you have something you'd like to show, plots, or if you'd like to show code or anything like that, that is possible. You can share your screen, and I'll demonstrate that here in just a moment. But if you have questions about how to do that, we can hopefully get it figured out. So the class I wanted to talk about, I'm teaching it's an upper division analytical mechanics course. And the course title is actually analytical mechanics, but I have decided to incorporate some very non-analytical pieces to the class, because analytical mechanics is fun, but all of the really fun stuff, in my opinion, is numerical, because the really fun stuff in analytical mechanics is nonlinear and chaotic and all sorts of exciting things like that. So what I've done, and then these students, so these are junior level students for the most part, mostly physics majors, although I do have a couple of engineers in the course who are physics minors. And about half of the class has had our junior level computational physics course, but the other half hasn't. Either they're not going to take it, or they just haven't taken it yet. And so that's been a little bit of an adventure. But what I decided to do this time around, and this is the first time I've taught this particular class, is for each homework assignment to incorporate basically a numerical solution of a differential equation. And I haven't required them to come up with the code. I've given them code that is sort of functional code, and then they've had to do something with it. So the last assignment we did was we're talking about chaos and sort of chaotic behavior. And so I've given them code to do a damp-driven pendulum, and then asked them to go exploring. So let me share my screen, and I can show you the the code that I've used. So can everyone see that? Yes? No? Okay, I got a thumbs up. Let me make it slightly larger so it's a little easier to see. This is Python code. I'm running it in the Spider IDE. That's because that's what we use in our computational physics class and a little bit in some lower division courses. So most of them have seen the interface before. And this is actually the code that I give them. So it uses the SciPy library to solve the differential equation. The differential equation for the damp-driven oscillator is already in the code. And so literally they can download this and they can hit run and it will generate a plot if my computer decides to cooperate, which it's not at the moment. Let's see here. Why aren't we running? Oh, there it goes. Can you see the plot window? No. Okay, let me figure out how to do that. There we go. This will give you the whole thing. So what we have here is 3 plots. So the 3 plots that by default pops up are the time evolution of the angle here. And if we zoom in a little bit, you can see that this is a fairly weak drive strength, and so it's basically sinusoidal. And it also pops up a plot of the phase space evolution, right? And I've got the initial transient behavior cut off here. So they can see that, sure enough, this phase space looks like a simple harmonic oscillator, or a damp-driven harmonic oscillator, I should say, which we've played with previously. But if I go in here and I give it a larger value of my drive strength, we can get into some funny things where it gives you definitely not simple harmonic motion or damped driven simple harmonic motion. We get this sort of funky business of running around phase space. Again, it's a repeating pattern. It's doing a single path through phase space, but now it's doing something a little more obviously nonlinear. And then, if you can give it something large enough, we'll see the thing will actually go chaotic, and you'll go through all kinds of crazy things, and it'll flip around and flip back and do all the fun stuff that chaos does. And so what I've done, the assignment really is I give them this code, and then the first thing I ask them to do is basically just, find me linear behavior. Then find me something that is not chaotic but is clearly nonlinear, and then finally find me chaotic behavior. And so they're not coding, they're just changing the code, but it allows them to play with the sort of nonlinear stuff and find chaos and do some of those things. And then some of them who have had some programming experience will, not because I've assigned it, but just because they're interested, take this a step further, and they'll look into, can I make a Poincare section, or can I do some analysis? But they don't have to do that. And then the last thing that I have them do is I have them add a second solution with slightly different initial conditions, and then plot both of them together to show that indeed you actually do see a divergence in the evolution of these systems. So they'll come back in, they'll add a couple of lines of code that just basically solve the differential equation again, but with slightly different initial conditions, and plot both of the trajectories on top of each other and show that, yes, this thing actually does lead to this diverging behavior in the time evolution. So so that's sort of what I've done. In terms of the results, so I've had, on each of my homework assignments, I've had something like this, where I give them a piece of code that is already functional. They have to modify it and play with it a little bit. Generally, it's been very light on the programming. The plus of this is that I feel like I haven't thoroughly lost anybody who isn't familiar with the programming side of things. The minus is that the people who are familiar, I feel like, have been a little bored with these things because they can get it done very quickly. Some of them have naturally gotten curious and explored on their own, but a lot of them have just said, okay, I can do that. I get it done in, 2 minutes, print out a couple of graphs and staple it to the back of my homework, and that's all I have to do. So I'm not quite sure how to deal with that sort of divergence of, or different initial conditions on my students. But by and large, I feel like from a course that is not designed to be a computational physics class, I feel like it's given them some tastes of some of the cool things that you can do computationally. So anyway, that's what I've worked on. Questions, comments, thoughts?
I like it. It looks fun. I'm going to be teaching that kind of course in the fall, and so yeah, I'd love to do that. I want to incorporate more computation.
Yeah. So the thing that I struggled with is how much programming I wanted to try to teach them, because like I said, some of the students, they don't know how to do any of it, and we don't really. I mean, myself and one other faculty member tend to integrate computational pieces into some of the lower division classes, but it's not uniform across the department. And so some of them have never seen Python before. Some of them have had courses on it. So it's sort of, I don't know, it's a bit of a mixed bag.
Nick, how many students do you have?
I've got 12 students this semester.
That's a good number. I'm wondering. I started out. Well, I actually started out in statistical mechanics back in history doing this, and then I very quickly I ended up teaching in alternating semesters, the statistical mechanics and this very course you're describing. And for many years I did this, for about a decade, actually. And that's where I started doing all of this. By all of this, I mean integrating computational activities. Probably at the very beginning, I was a little too ambitious. But from the start, and I really didn't ever deviate from this, I started requiring them to actually code things from scratch. And now, you've probably heard me describe this before. Back in around, you see, I started doing this in '93, believe it or not. All right, so now I just gave away my age to all of you. So, although maybe not, plus or minus a few years, I'll leave it to you to calculate. We should make an exercise set based on Ruth's age, by the way. So I back then and up to about the year 2000. Students came in knowing how to program because they had all had basic programming in high school. And honestly, I didn't have to teach them anything. They knew what a loop was. They knew how to. I know what a loop is. Yeah, they knew how to up that. That's my weird 10-year-old speaking there. They came in and they knew what a loop was. They knew how to update things. We didn't plot anything. We didn't have these cool interpreter type of program, so we had to use a separate program to plot things. But anyway, my point is, I never had trouble getting, even in about the year 2000 plus or minus, when the students coming in no longer had programming and you actually had to teach them things. I always found it wouldn't take too long to get them actually into it. Almost like the approach you've taken, giving them a working thing. And after about 2 or 3 of these, then just saying, okay, you do it now, and using what they've been given as a template, especially if it's repetitive, like solving a differential equation for a different system, right? And so you might give it a try, and even not be afraid to make them actually do something. It doesn't have to be more complicated than maybe Euler-Kromer, for instance, right? But maybe try something. Use that solver as a check, perhaps. Use it as a guide, maybe, because that gives them the answer and they know what to expect. And then just say, now you do it. Something you could try. That would certainly probably keep the students who do have programming under their belt, keep them from getting bored. It would add a little extra challenge to those who haven't. Maybe too much of a one, I'm not sure. But like I said, I never had any trouble getting them into it. Now, I did expect this of them, though. And maybe that was the difference. But so it's just a suggestion you could try. If you are you teaching it again?
So I'll be teaching it again next fall.
Mm-hmm.
So we'll give it another try. I've actually taught so we used to have 2 halves of this course, and I taught the second half.
Mm-hmm.
But the second half was optional, and I found that I got a lot. The students who took it tended to be the ones who they tended to take it their last semester, and they'd already had the computational class, and so I could just assume they had.
Mm-hmm.
And actually, the first 2 weeks of this 2 homework assignments of this class, I was requiring them. I gave them a template and said, "Code it yourself," and had half the class upset with me. Actually, a quarter of the class was upset with me. A quarter of the class had no idea what was going on, but had a friend who would just tell them, "Oh, type this," and now it works. So, yeah, I don't know. It is a little interesting because I've done things like this in my intro mechanics class, so freshmen, and they don't actually push back as much.
Interesting.
So yeah, I don't know, but of course I was having them do different things. The freshmen, I mostly just used it for generating plots and doing a little bit of basic integration and things like that. So. All right, well, that's my story. Anybody else want to share?
Sure, I can share. So I had a pretty good semester. So I've been teaching, like an introductory mechanics, freshman level. The thing about it is that it's mostly computer science students. That it's about 90% are computer science majors, actually majoring in game design. And then the other 10% are applied science students, so either chemistry or physics. So they're kind of in the minority, but yeah, I just said from the beginning we're going to be doing simulations in this class, and we're going to be doing it in Python. And a lot of them were just really excited. They said, "Oh, Python! I'd love to learn it. I didn't know about it." Even some of the ones that hadn't had it before. Well, almost no one had experience in Python before. So it was great to get that encouraging reaction. Actually, just when I was planning out my course, I figured out that we had about 2 weeks left, just the way I had arranged it. And so I wasn't sure what to do. And based on Todd Zimmerman's encouragement, I just decided to make that a final computational project. So then I had to get them to there. And so I think I had 7 or 8 computational activities that would be sort of not in place of lab, but in place of discussion section. And some of these I'd made before, but I had to make probably, 4 or 5 new ones. And it was pretty amazing what they could do. And now they're working on final projects. They're almost done. And I'm really excited. So one student, or a group of students, they decided they wanted to make a simulation of the solar system. And they blew me away. So they had this idea, And then over the break, they just were like, oh yeah, we think we're done. We kind of have it. They had all the planets. Like, oh wow, that looks good. Well, then they went a lot further, and in the next week, they now have skins for all the planets. So all the planets like look correct with like the Jupiter's red spot and the Earth. And now they're spinning correctly on the right axis, and they got all the data off NASA to do this. And it's pretty awesome. And yeah, another one, they wanted to do ragdoll simulations. And I thought, okay, well, this is going to be a little bit challenging. We're going to have to do, moment of inertia tensors now and figure it out. And once I showed them the math, a student said, no, I still want to do it because I'm in linear algebra and this is exactly what we're doing. So I'd love to apply it. But even the students that I thought weren't very strong still had fun with it. So some other students, trying to think. Oh yeah, I thought they weren't very strong, but they're still making like cannons shooting at targets, or they're a pool table. Anyway, a lot of really cool ideas. I was very happy with it. I don't know, any questions?
So I'm curious about the stuff you did before the project, because the project sounds really cool. So how did you get them there?
Okay, well, let's see. I had a day where I called it, let's see, I'm calling it simulation with forces here. Remember what the lab was. I'll get out of this. Okay. Okay, so I had a glow script introduction. So that was just how you put a force, basically how you do Euler-Kromer. And then I added on if there were, so I had them explore different kinds of forces. So if you have a force that is constant, what does that do? Well, that's like projectile motion. Okay, well, what if you try a force that is proportional to velocity? Oh, it like speeds it up. Okay, what if it's negative proportional to velocity? Oh, it slows it down. What if it's attracting toward the center, and different strengths of that? And so they just kind of looked at what are the different orbits. And it's again programming Euler-Kromer, because I didn't give it to them. I said, remember that thing we did to make it work? You need to do that again. And so I would write the equations on the board, and they'd have to translate that into computer code. I consistently did that, and it was really surprising how consistently they still didn't remember it, but once I wrote it down, then they'd have to type it in, and then it would work. So I mean, I would write it down in math, and then hopefully they would get it into computer code and help them with that. Then there was another one where we were looking at gravitational forces. And so this comes right out of the Matter and Interactions book, where you have something start in orbit. So it's orbiting around the Earth, and so you look at orbits. And then you have put a moon, which is just actually a fixed mass. And they want you to have it where it goes around and then loops around the moon and comes back. And so they say, well, how do we figure that out? And I say, well, you just guess and check. And they said, really? Like, yeah, you just guess and check and see what works. And I wanted to 5 digits of accuracy, by the way. And they think, oh man, but it doesn't take that long for them to guess and check. And it's actually kind of fun. You can set the camera to follow your little rocket as it moves around. And so it's kind of a fun thing. Let's see, then what did I do next? A couple weeks later, I did a harmonic oscillator simulation, and then I had them make it damped as well. And I think, did we look at energy? No, we didn't look at energy that time. And then I have something that I call the energy graph activity, where it will show an energy graph, like, the potential energy as a function of position. And then they also have to plot what is the kinetic energy and the total energy. So they see the total energy as this line, and they can visually see how, when it gets up close to the total energy, it's really slow. And when it touches, that's a turning point, and then it goes back. And then they have to come up with, well, what's another potential energy function that could look cool? And some of them get really crazy. Actually, the varying force one too, I also had a creative element, like program in some force that looks interesting. And so they get really crazy. They'll just throw in cross product. They don't even know what it means. They'll just throw in a cross product, or also just, hey, how about one that changes with time? And so they get their own driven oscillator, essentially. Let's see. Yeah, and then later on, I had them do, or was it driven later? Oh, I see. They had harmonic oscillators just by itself. Then later I had it damped and driven. And then I had a seesaw lab, so I was getting in rotational motion. Oh yeah, so rotational motion simulation, seesaw simulation. There's a Rutherford scattering, which is out of the book, but that's fun too. And then finally I had them do collisions, hard sphere collisions. It's a bouncing ball simulation. And yeah, I feel like I was managed to make them so they all fit within the 2-hour time period. And basically everyone could feel successful at the end. I was really happy with the last one because I had basically the whole thing programmed. And I said, everything is programmed in there. All the movement. The only thing that is not programmed are the collisions with the walls and the collisions between balls. All you have to do is figure out what to do. And so I'd explain to them the math. And so they would figure out collisions with a wall with a varying coefficient of restitution. So not just 100%. And so they'd figure that out within 15 minutes. And then they'd spend the rest of the time figuring out the other one. Even though I explained to them in a paragraph what they need to do, they needed to work out the algebra. And they were really, really like filling out paper and trying to get it to work. And then finally they get the impulse and then they apply it. And then it's kind of a triumphant moment. And each of the groups was able to get there. So that was really fun. And so then they used those previous as templates, I think, for their final projects. I don't know, but I don't know what accounts for their positive attitude. I think partly saying this is what we're doing and not being apologetic about it helps. I noticed when I first started teaching, I was kind of apologetic. Now this is dumb, but I was teaching physics 2, so electricity and magnetism. And someone had told me, oh yeah, they have a hard time with vectors. And so I was kind of apologetic that, oh, we have to do vectors. And then it was horrible. Like certain students felt like they didn't actually need to learn vectors. They were resistant. So the next semester I said, everyone needs to learn vectors. And if you don't know it, we need to learn it very quickly. Like this is very important. We'll be using it all the time. And I did that and then I had no problems. So I think the same strategy could be for simulations. You just say, hey, this is a part of physics and we're going to do it.
So I'll ask another question. I don't mean to monopolize, but there we go. So you've got these students in lecture, and then it sounds like you have a lab and a discussion.
Yes, yeah. So there's 3 hours of lecture. There's a 2-hour lab and a 2-hour discussion. And so I would use the 2-hour discussion some of the time for simulations, and some of the time they take a unit test. So I'd give them 2 hours for that, just so there'd be no time pressure.
Dan, what class was this again? I'm sorry.
This is freshman level mechanics.
Okay, so they're all right. Gotcha. That's what I thought.
They typically take it their sophomore year.
All right.
Yeah, and many of them are computer science students, like I said. So they have had computer science 1 and 2 before taking this.
Mm-hmm. And how many sections do you all teach of this?
So I'm teaching 2 sections combined. So they're combined for the lecture, but there's 2 different lab sections.
Mm-hmm. But there's other sections too, I presume.
No, I'm the only one who teaches it.
Okay, gotcha. So you can.
Yeah, just because they have now shifted all of the engineers to taking statics and dynamics, they don't take this course.
Oh, is that right?
Yeah, yeah. So it only runs once a year in the fall. So
I see. Gotcha.
Yeah.
So okay, that's interesting. Okay, so then you can do whatever you darn well please, I guess.
Yeah, whatever I want. There's no one else. I can just do whatever I want.
Yeah, and then you pass them off to somebody for E&M, I guess, right?
Yeah, well, and that's Todd Zimmerman. So he's hitting them. Well, what happens is most of those students will never take physics. The next physics class, the computer science game design students will take is my basically programming a physics engine. Gotcha. So that's the next class they will take.
Yeah. Okay. Well, that's a nice luxury then, being able to have so much flexible time, as well as not a prescribed curriculum of stuff you got to get to, right?
Sure. Yeah, and a supportive department.
Yeah, because as you know, we encounter a lot of professors who just don't have the flexibility and the freedom to do these kinds of things, and so we get a lot of questions about how do you make this work when you've got the canon that my department has deemed we must cover. right?
Yeah, yeah.
Okay, interesting. Well, I think that I think that's the right approach, is to tell them this is expected, and I imagine you also keep it fairly upbeat too, so that helps with the
Yeah, I
attitude.
try to tell them how cool it is and
Yeah, yeah,
see
sure.
some good stuff.
Yeah, well, good. Sounds like a fun class.
Thanks.
I mean, just think about that experience. I gave it, this little this other little webinar thing we did last. I've been giving talks like this about the intro courses, and I've actually, to some consternation, I've told people that if you're still sliding a block down an inclined plane in your mechanics class, you're doing your students a great disservice. And so think about the experience having gone through this type of thing versus the traditional mechanics course with all the analytical stuff thrown in. And think about the enhanced content coverage that you're able to accomplish
Hmm.
with them, right? Uh, it's just a different experience altogether. And so
Yeah, the one thing
yeah, go ahead.
I would say that I didn't do is I did not put this on the exams. So it was, I think, I don't know, it kind of set that up as like, oh, it's something you do in these lab sections, but there will be a final project. So yeah, I don't know. One time I did put a question that was not coding, but it was related to what we learned in the discussion section. And they were completely surprised. Like, oh, we have to actually understand what we're doing. It was just about coefficient of restitution, about a ball bouncing off a wall. So nothing even really hard, but just what does coefficient of restitution mean? And I was shocked how few students actually understood it in an analytical sense. They programmed it, but it was kind of out of sight, out of mind. The computer will do it now. And someone even wrote a protest on their test, like, we only did this in lab, so I didn't think it would be on the test, even though I gave them the objectives and I explicitly said this will be on the test.
Well, yeah, well, there's always room for improvement, right?
So I'm interested in. It's nice to hear about this. So I'm going to be teaching the intro freshman level mechanics
Yeah.
next semester, and most of my students will be engineers.
Okay.
It's about we're sort of 90% engineers, and then a smattering of computer science, physics, chemistry, geosciences majors. But it's almost all engineers, and so what I'm going to do is I'm going to actually make a computational component to each lab. And those may be as simple as you just have to generate your plots. But you're going to have to generate plots. You're going to have to do things. So
using Matplotlib or something, or
yeah,
SciPy. Yeah.
Yeah. So I'm going to make them do it in Python, actually, for the most part. And so anyway, it's interesting to hear experiences. So how important do you think it is that your students were mostly, had a computer science class or two?
I think it helps get things running from the beginning, that they know what a for loop is, they know a while loop, they kind of get the idea of what computers can do. And so I think that helps. And so having sort of the majority of the class say, oh yeah, really helped the others. I don't know if anyone was hesitant. Although the other students that weren't computer science seemed pretty on board. I had one other semester where there was a student who was just really resistant to it. And he felt like he didn't need to learn it. And he was just trying to, actually, like, two students that were just kind of like tagging along and would just leave their partners to do everything. It's like, well, wait a second, like, you need to learn this. And he's like, it's okay, I'll just take zeros on it, I don't care. But that wasn't an option in this case. But I didn't have anyone with that attitude. I even looked, I said, if you've never done this before, like, let me know. How many of you are there? Like, don't be shy. And a few people raised their hand, like, but I want to learn. I'm like, okay, that's great. I'm going to make sure you do learn.
Any other questions? Great. Well, Daniel, thank you. Yeah.
Yeah, I'd be happy to share these labs or, you know, those computational activities.
All right. Would anyone else like to share something that they've worked on, tried, succeeded brilliantly, failed miserably at?
Sure. Yeah. Oh,
Go ahead.
okay. So it's actually quite interesting to hear your experience, and I recognize a lot of my own experiences. So this semester I'm teaching computational content actually in 2 classes. One is modern physics. That's a 200 level class for our physics majors. That is going quite well, I would say. But the one I want to talk about is the University Physics Lab, University Physics 1 lab course. So it has a kind of special situation. I don't actually teach the class. I'm the lab coordinator. And it's a course that accompanies the lecture. It's a calculus-based freshman lecture. But technically, the lab course is a separate class, 1 credit. And we have our graduate students, mostly masters or some PhD students that are actually teaching the classes. So the challenge is, of course, how do I teach the content when I'm not teaching the class? So, and I've been doing this a few times now. So we start with, we actually make the students do some coding, but at first it's more or less copy some existing code from some cells where we're using Jupyter notebooks and use Python. So we make them copy or modify some code. And the first thing they do is we teach them about a little bit about statistics, how to calculate the standard deviation of a bunch of measurements and uncertainties. And so we replicate those calculations in Python. And then we get them to actually plot a histogram of the values. And then in the following labs, so there's one about projectile motion, where we have them plot trajectories for different launch angles. And then we have a lab about free fall with air drag. And so that's where we introduce them to Euler-Kromer integration. And then one lab about a simple pendulum, again, Euler-Kromer integration. And there we have them explore what happens when you start not at small angles like 5 or 10 degrees, but at 60, 70, 80 degrees of initial angle. So experience has been somewhat mixed. Initially, the responses were quite negative. So something from, it was actually this spring, one student wrote, coding should not have to be part of a physics lab class. I get nothing from the computational component of the labs. I have no desire to code, therefore the coding portion mostly hurt my grade. Or another student, the lab reports were enough work, so add coding on top was gross. So we did over time a few tweaks. For example, introduce coding really early, that is in lab 1. And I also worked on better training my teaching assistants. Another benefit is that since I'm also doing coding in modern physics and later in E&M, we now have a bunch of Python coding trained physics students who serve as tutors. So that's helpful. And so just a week ago, I did the survey for this fall. and the responses are beginning to look not all positive, but definitely a lot better. So one student actually writes, I enjoy the computational aspect of the labs. It helps me familiarize myself with a number of different skills. Another student wrote, as a computer engineer, it was cool to see other applications of coding other than circuitry. I should have mentioned, by the way, about half, at least maybe 2/3 of the students are engineering students. And then the rest are some physics majors, meteorology, earth and atmospheric sciences. So as far as implementation, we're using Jupyter notebooks, and I'm using NVGrader, so that we can handle the larger number of students, because all in all, across the 4 sections of the lab course, it's about 70, 75 students. So yeah, that's my experience so far.
I'm curious about the NVGrader. So how do you typically have it evaluated? Do you tell them to, I don't know, make the answer equal to a variable of a certain name, or do they write functions?
They do write functions in some of the labs, yes, and so for some, I actually wrote test cases so that that NVGrader automatically checks whether the function returns correct results. Other things like plots, obviously, they have to be manually graded.
Okay.
But definitely NVGrader is quite helpful, and the newer versions, 0.6, that came out not so long ago, actually I think it was just at the start of the fall semester, which I haven't deployed yet, but that one makes it easier now to return the feedback to the students.
That's good to hear. I might use it in the fall again.
So I had a question about the, so like, for example, on the you mentioned one that had to do with air resistance. Were you doing air resistance on free fall or projectile motion, or, I mean, so just one?
Free fall. So we have the students drop cupcake liners, and they can stack them so that you have essentially the same cross section, but increasing masses. And then the students use webcam and video analysis to actually measure the position versus time. So they do have the experimental data, and then they can compare their computational result against the experimental data.
I think we had a hand up.
Yeah, so I was just wondering, and this is not just a question for Axel, but for everybody generally. In these intro courses that you're talking about, the students that when they come and you do this Euler-Kramer or whatever, have they seen these methods in a different class before? Have they had a calculus experience before, or is it just, you're just plopping it onto them?
So in my course, no, they have not. In fact, the vast majority of students have never coded ever in their life.
Well, my question was not about the code, but about some background calculus. Like, have they taken calculus before? Like, do they know that kind of?
So it's a calculus-based physics course, although in University Physics 1, that usually means that about half of the student has had calculus before and half of the student is taking it along with the class.
Right. So I mean, I'm kind of in a similar situation where I try to do computation with my students, and oftentimes when I try to talk about these different kinds of methods, students' pushback is, well, we have not done calculus, and I'm in a service department with like service physics department for engineering majors, and I'm not sure how much of our calculus material is really at par with other universities, and that's why I was wondering about but I'm in a similar situation, and I feel like you are already most of you are doing a lot of material that my students would just say that this is too much material at this level. So I don't know.
If I can chime in, I've had a similar experience with my students. I actually sat in on their Calculus 1 class one semester, and they did spend about half a day on the Euler method. They were not doing Euler-Crommer because they weren't even doing second order differential equations. Basically, the calculus professor said, oh yeah, you can, if you're in a hurry, you can approximate the derivative with its slope. You can linearize it. It's okay to do, but you never really want to have to do that. And they were kind of putting it down, like not to deride how we do it in physics, but just to say, this is not a thing we're interested in this class. And I was kind of sitting there twitching in my seat saying, no, we use this all the time. Don't put that down. But they definitely never did any kind of coding application with it. They might have done like a table with it or something. But so even if the students remember doing it, they didn't have a terribly positive experience with it.
Thank you.
So
I would just.
Oh, go ahead.
Oh, sorry. I would just chime in that I think you can tell them that the Euler method is a way of doing this. This is what I say, without knowing differential equations. That we're just doing algebra. We're just adding and dividing and multiplying. And if we do that enough times in a small space, well, yeah, infinitely small, that would be calculus and differential equations. But this is a numerical way to do it, so you don't need to know differential equations. You can just do simpler math. So that's kind of how I try to motivate it.
I think that's a great suggestion. The issue, again, I will probably go back to what Kelly was mentioning earlier about the amount of freedom that I have in my course. I am teaching a University Physics 2 course this semester where I have to cover wave motion, optics, static electricity, magnetism, and circuits. All of that in 15 weeks of classes, and it's basically a lot of material that the students have never seen before. And so on top of that, if I want to give them, and I can actually tell you a little bit about what I have been doing, when the time comes.
So I'll just add that I regularly, so when I try to do computational things in my intro mechanics class, which is mostly engineers, most of them have never programmed anything. They think they know because they can operate like Instagram, but they've never programmed anything. And I am fortunate in that we require Calc 1 as a prerequisite to our intro mechanics class. So everyone nominally has taken and passed first semester calculus. Some of them are still petrified of the word integral, but most of them will not run screaming if you say the word derivative. So I've done some things where, for example, when we talk about pendula, I've done, well, okay, a pendulum is approximately a mass on a spring, right? It's approximately a simple harmonic oscillator, but not quite. And so can we explore the difference a little bit? And I don't even tell them that they're solving a differential equation. I just say, look, you cannot solve this analytically. Like if you take this over to your math professor, they won't be able to solve it analytically either, but you can approximately solve it, and here's how. And computers are really good at this. And I find that I get less pushback if I don't tell them, oh, we're going to solve differential equations, because they think that's mean and scary and they don't know what it is. If I just tell them, this is a tough equation. You cannot solve it analytically. You can't write down a function that is the solution to this. However, you can use a computer to approximate it. And here's how. Then they tend to think it's neat. On the issue of fitting it into curriculum, that's a big challenge for me too, because usually we have multiple sections going. We're all supposed to get to the same place. And you know, if I take time out to do more computational things, obviously I'm doing less of something else. The happy medium for me there is mostly, I try to use computation in a sort of supplemental role. So for example, I don't care if they learn the Euler-Kromer algorithm. I don't care if they learn the sort of computational pieces. What I want them to be able to do is to understand that if they have an equation, that they can solve it on a computer. They don't have to understand. It can be a black box for the solution method at this point. But they can solve it on a computer. They can plot it. They can compare it to an experiment, or they can compare it to a theoretical prediction. And that's good enough for me.
Yeah, thanks for that. That's actually what I have been doing in my course so far. Like every time I do something, I show them you can use the computer in a way, like just even as a calculator, probably a little bit better than the calculators that you take with you.
Okay, well, we have a couple more minutes if anybody would like to share one last thing quickly, or if not, we can end here.
I can try to go quickly. So
Go
I did
for it.
I did a little revamp of my Physics 1 intro mechanics with calculus class, where every week featured an integrated activity that included both a lab matched with a coding activity. So rather than throwing at them a lab and throwing at them a coding activity that I hoped would be similar, I made them explicitly about the same project or the same activity. So on the week that we did projectiles, they did a projectile experiment, and all the experiments were done in Tracker this semester. So this is my first semester working with Tracker as well. So they would have to get a video of the projectile going in the air. They'd have to do all their Tracker analysis. Then they'd have to turn to the code. And basically their goal was get the animation and the graphs from the code to match the video and the graphs from the experiment. And we had the same kind of procedure every week. It was literally just a different subject. And they seemed to enjoy it. They definitely liked it better than having everything be disconnected in terms of I learned one thing on Mondays and another thing on Wednesdays. And for the most part, their activities were successful. They were able to get things to match up. So like on the projectile lab, they would have to figure out what drag coefficient would get their projectile motion to match once they had the the launch angle and the launch velocity correct. And we did similar things to what y'all talked about, coffee filter drop, mass on a spring, mass on a pendulum, things like that. The issue that I ran into and that I'm going to look into trying to improve next semester was in their write-ups. They would each write about a couple of pages, which is all I really expect of them. I'm not, we don't do formal lab reports. We just do a letter home to your parents, explaining to them what you learned in physics this week. But inevitably, in every single one of their write-ups, they would spend about 3/4 of their writing space, however long they took, on the experimental portion, and only maybe about 1/5 of it on the coding, and then the last little couple sentences on the comparison between the two. And I was really kind of expecting that to be more like 1/3 and 1/3 and 1/3. And I think part of it is that even though we were using VPython and we have this, we have the code written in front of them and we go over every week how it works, they never really explained to the reader how the code works or what they got out of the code. Like they never included a screenshot of the graphs. They never included, a description of, oh, there's a peak at the same time here, there's a peak at in the lab. And I don't know if that's because they think of the experiment as being more real than the coding or more important, or if it's just that they did the experiment first in the week. So I don't know. I'm looking to see how I can expand that, because obviously I would like to be able to better assess what their understanding was of the coding portion of the experiment.
I had a question on that. So, so you had matched computational. So they were basically simulating the same thing they were doing in lab.
Right, exactly. And since all the labs were dynamic in nature, they could have, you know, an animation to graph to try to match with at the end.
That's neat. I had one lab the last time I taught that class that I tried to do that with, and this may not be possible for all of them, but that one lab that I had working, I actually made them put their experimental result and their computational result on the same graph.
Yeah, that would be wonderful.
Which takes a little bit of doing sometimes because, well, initial conditions get tricky. But
yes.
but if you can, but for me, in that one case was simulating a pendulum. That actually, they really liked that. They really liked that the computer would actually give them. Actually, the computer gave them two results. The computer gave them one that matched a damped harmonic oscillator and one that matched a damped pendulum. And their job was to show that a real pendulum looks like a damped pendulum, not a damped harmonic oscillator. But so I don't know how that would work with all of them. But if you make them put them on the same graph, then they have to compare them.
Yeah. I might give that a try, or at the very least get them to copy paste the screenshots on top of each other. There is a way of importing external data into Tracker. So if I could have them export it from the VPython, I could have them import into Tracker, and that would probably be easier than the other way around, I'm guessing. But yes, picking the topics was a bit of a challenge. I had to really rearrange how I did the topics. I had to throw a few things out. I had to spend a little bit longer on some things just because, you know, like if you're doing a free body diagram problem, those are usually static in nature. So I had to get a little bit creative with how to figure out how to do that.
I actually had a question there. Were all of them dynamics? You didn't do one. They were all time evolution problems?
Yes. That meant that some of them were a little bit simplistic. So like the first week was, let's just start with constant velocity, which I used to loathe doing a constant velocity lab because I'd say, no, let's skip to something interesting. But the subject for that one was they had to video themselves walking. And so they had to get their own, walking speed off of Tracker, which is a useful exercise because you learn that human walking speed is about a meter per second. So now they have a context for a meter per second. And then they go and model that. Well, modeling that is, we see that as trivial, but it's their first time seeing, for most of them, it's their first time seeing a computer code, first time seeing a loop. And then they've only got one update to do, right? They don't have to update an acceleration. They just have to, they don't have to update a velocity. They just have to update a position. And so then we build on that the next week with adding forces and acceleration into it. But no, yeah, every activity was dynamic. And I think they liked that aspect better. I think a lot of times they do these, sort of static experiments. They get, a reading off of a force sensor or something, and that's nice, but I think they like having something to actually look at and watch.
That's interesting because I'm trying to implement something similar this next next spring, and one of the ones that I'm really having a hard time with is figuring out how to do something computational for the statics portion, right? Static equilibrium, which our engineers really care about. In fact, they yell at us because then the engineering students go on and have trouble in their statics class, and they say, "Well, you should have taught them statics." And,
I've had the opposite experience. I had a well-meaning engineering professor tell me that the students can't really learn free body diagrams or statics problems in a physics class, and I sort of said, "Okay, I'll leave that up to you then, and I'll teach what I want to."
Any other questions? All right. Well, our hour is up, so maybe we'll end here. Thanks for for those of you that shared. And
Yeah, thanks a lot for coming out and sharing. Very good. Very interesting stuff you're all doing.
And I imagine we'll probably do another one of these in about 1 semester time. So, you know, do something interesting next semester, and we'll come back and talk about it then.
Yep. Yep. All right. Good night, all. Thanks,
All right.
Nick.
Thank you,
Good
Nick.
night.
Good night.
Bye.
Thank you. Good night.